Okay, good morning again. So today we will discuss about the reanalysis. So we have one, not only one, we have two reanalysis. We produced at NCMRWF. One is the regional reanalysis, that is IMDAA, Indian Monsoon Data Assimilation and Analysis. And yesterday we discussed the website and what are the different variables available and how to download. And there are some issues, all those things we discussed. So today we will see what are the different types of data we used in the IMDAA regional reanalysis, because the same data we used in the global reanalysis also. Because it is the global thing, and why we are more focusing the regional reanalysis. This is the first of its kind, and this is the satellite era regional reanalysis over the Indian monsoon region. And this is for a longer period from 1979 to 2020. Initially we were planning up to 2018, but afterwards we extended to 2 more years up to 2020. And now for the continuity we are providing the analysis from our operational model over the IMDAA domain for the continuity. But if you see the reanalysis, it is from 1979 to 2020. Afterwards it is analysis, but you can use that as the continuous data, because the analysis whatever we are providing in the IMDAA site is from our update run. So we do the operational run in each assimilation cycle twice. 0, 6, 12 and 18. So yearly run and update run. So yearly run, because we have to supply the initial condition and other post-processed forecast output to the various users before, means there is a time limit. So within that time limit we have to provide all the data. Because of that, almost all the operational centers, they do the assimilation and the forecast like yearly and update cycle. So yearly run we use only the limited number of observation that is available, and we do the forecast whatever the forecast length, whether it is 3 days, 5 days or 10 days. And later on, when we get almost all the data, we do one update assimilation cycle. But we do only a short forecast based on that update assimilation cycle, not the long forecast like 10 days or 5 days like that. And again for the 6 UTC, the next assimilation cycle, we use the initial condition from this previous update cycle. So the next cycle will means get all the information from the available observation, that is part of the first guess. So here actually IMDAA is a collaborative project. It is it was the project under the National Monsoon Mission of Ministry of Earth Sciences, and it is a collaborative project among NCMRWF, IMDAA and UK Met Office. As yesterday we were discussing that at NCMRWF we are using two models. One is the GFS, NSUB GFS based system, and another one is the Met Office UK unified modeling system. So in this IMDAA regional reanalysis, we use the unified modeling system, and we used the 4D system of the unified modeling system, all those things. So it is a collaborative project, and it is funded by the Ministry of Earth Sciences National Monsoon Mission project during the phase 1. So now I think this room, everybody knows what is data assimilation, all those things. So why do we need data assimilation? Sir already explained in the morning that why do we need data assimilation. So for the completeness, I am just giving again an overview. So we have the model. Model is the complete description of the atmosphere. We know that if we take the first guess, we have the information at each and every grid point. So that is why whether it is correct or wrong, that we are not checking right now, but we have the complete description of the atmosphere at each and every grid point. But the errors grow rapidly in time. That is what the model, whatever we are having the representation from the model. Then we have observation, but we don't have observation at each and every grid point. It is the incomplete description of the atmosphere, but bring up-to-date information. Whatever the observation we are having, that is the up-to-date information. If we are neglecting the instrument error or whatever that measurement error, all those things, then we can consider this observation as the error-free kind of thing, or the up-to-date information. But we don't have the complete description of the atmosphere from the observations alone. But we have the complete description of the atmosphere from the model alone, because each and every grid point we have the values. And so the two things we are having, one is the complete description of the atmosphere, but the error grows rapidly in that system. And other one is the incomplete description from the observation, but the system is not even though the information is up to date, it is incomplete. So the data assimilation, it combines these two sources and produce an optimal or the best estimate of the atmospheric state. So that's what data assimilation does. So the state we call the analysis is used as the initial condition for extended forecast. So these are the things happening in the operational or when you are doing any experiment, so that we are generating the analysis and then we are doing the forecast. So for the operational NWP assimilation system changes when assimilation method and assimilating models improve. So if you consider NCMRW, so we implemented unified model at around 2009-2010. So that time it was the 25 kilometer resolution for the were alone. We were not having any ensemble system. Then afterwards in 2012-13, we introduced the ensemble system and we changed the model resolution to 17 kilometer. Then afterwards again in 2016-17, we introduced the hybrid 4D one. So if you see, the model resolution is changing, the assimilation system is changing. So that is what happening in the operational environment. We are not using the fixed system throughout the period, because whenever there is an update, whenever we require the higher grid resolution or better data assimilation technique, we change that one. So that is what happening in the operational system. The data assimilation system changes. This is what the data assimilation system changes when assimilation method and assimilating models improve. This creates discontinuities in the analysis from one system to another. So when we, suppose if you are using the operational product or the operational analysis from NCMRW for any other operational center, what you are getting is that 2009 to 2012, you are having only 4D VAR. Then afterwards we have the hybrid 4D VAR, and then again there is changes in the grid resolution. So the system is not continuous. So what you may have some, you get the data set continuously, but there is changes in the assimilation system methods and the assimilating models. So that is what happening in the operational environment. So then what is reanalysis? So operational environment, these things we cannot take as the continuous data set. So in that case, when we want very long time series of atmospheric data for climate monitoring, all those things. So in that case, we need reanalysis. So we have observation, we have NWP. So what is happening? We already explained that observation, it is not available everywhere. It is limited variable. We don't have all the variables that we observe. Then the physical consistency of the observation. So these are some of the limitations. And if you see so we cannot use this for the very long time series of atmospheric data and for climate monitoring. And if you have some observing system for a particular region for long term, you can use, but that again, it is limited to that particular region or that station, something like that. So we cannot use this observation alone as the long-term series of atmospheric data or for climate monitoring. When we come to NWP, that we already discussed, that system changes regularly. Both the data assimilation method and the NWP model changes regularly. So the data set is not continuous, and variable quality, because we are changing that 4D VAR to ensemble 4D VAR and we are changing the resolution. So the variable quality output we are getting. So in that case, we cannot use this NWP operational product also for this very long time series, because there may be a jerk in between, since we are changing the assimilation system and the model. So you know the analysis. Analysis is an estimation of the most likely current state of the atmosphere given observations and previous forecast. Then what is reanalysis? So analysis and reanalysis, it is almost same, but in reanalysis, that is similar to analysis but for a historical period. So we are doing actually this IMDAA. If we are telling that we were discussing that IMDAA is from 1979 to 2020. So we started running from 1979. So we are not running that at 1979. So we started the IMDAA reanalysis at 2016-17. So from that period, we started running from that previous historical period from 1979. So reanalysis is not that current real-time run. It is the reanalysis is similar to analysis, but for a historical period, usually for a long series of reanalysis and produced using a frozen system. So frozen system means in the reanalysis, we fix the data assimilation system and we fix the model also. So in the course, so suppose the 40 or 42 years of reanalysis, we don't change the model, we don't change the data assimilation system. So the system is consistent. So whatever we are having, this we use the consistent system, then we do the analysis, or means again it is same as the assimilation. So we do the analysis. So that's what it is called reanalysis, because it is the analysis of historical data during that period with a frozen system. So these are the basic differences between analysis and reanalysis. In analysis, the system is changing continuously. Whenever there is an update in the data assimilation or in the model, so the operational agencies changes the system. But in the reanalysis, whoever is doing, even ECMW of NSEP, NCMRW of GMA, whatever they are doing, they fix the assimilation system, then the model also, then afterwards they do the analysis or the assimilation for a period of long time. So reanalysis provides comprehensive snapshot of atmospheric conditions at regular grids and intervals over long time periods, whereas observations alone can provide only a limited understanding of the past weather and climate. So this is what reanalysis. In a nutshell, both analysis and reanalysis are one and the same, but the difference is reanalysis is the historical data assimilation with a frozen system, and analysis, it is the operational condition or the real-time condition. So whenever there are changes in the model and data assimilation, we update that one. So what are the aims and uses of reanalysis? So we already discussed, it is the frozen modern data assimilation scheme. So if you see in 1979, we were not having 4D-VAR system. So that time what we were using is only the optimal interpolation or Cressman technique or something like that. So the 4-dimensional, the variational method was not there. So here we are using the 4D-VAR method. So that historical data, so we are using the modern data assimilation system. So we can, that is the advantage of reanalysis. So we can produce the reanalysis for the historical period using the modern data assimilation system. So in IMDAA, we use the 4D-VAR method. So the best use of appropriate available observation. You see, yesterday when we were discussing, I was telling you that at NCMRWF we are using 6-hourly assimilation cycle. So 6-hourly assimilation cycle means we are considering the data we are getting between plus or minus 3 hours. So sometimes the plus or minus 3-hour data we may get late. We may get the data in the next day, or maybe some after 10 days or 5 days due to some reason. So in the operational setup, we cannot use this data anywhere. So, but in the reanalysis, there is no cutoff. So we have to take the time of that observation. But when we receive that data, that doesn't matter. So if the data is there, we can use in the reanalysis. So that is another appropriate, means it is advantage of reanalysis. There is no cutoff. And consider using more observation that operational analysis, produce a long-term series of reanalysis. Usually it is for decades. And what are the uses of this reanalysis? It produces scientific resource, validate models, study use of observation and assimilation system, historical weather events, and study large and small variations in weather, predictability, produce weather statistics, extreme events to lead into operational climate monitoring, and link to observation record to climate models and AML and data science. Because if you see the data science or AML techniques you want to apply, you need a long, because first you want to train the model. So for training the model, you want a long-term series of data. So if you have the 40 years or 50 years of data, then it is a good enough, this is a good source to train your AML or data science model. So this is another application of reanalysis. Then who are the user communities? Scientific and modeling community. So they use the reanalysis data as a proxy for truth for initialization or as a boundary condition. So if you see, many of you people may be using IMDAA and ERA 5 data. So you are using the reanalysis as a observation. You are considering that as the truth. You may be running your WRF or any other model, and you may be comparing the output with your truth will be either ERA 5 or any type of reanalysis. So that is one of the application, because it is the continuous data set and we can use, there is no cutoff, and we can use almost all the available data. So that can be considered as a truth, and you can initialize your regional model with the regional model and global model with the reanalysis also, like initial and boundary condition. Then observation community reanalysis for data quality monitoring. So how the quality of data, suppose some satellite instrument, how the quality of the data is deteriorating with time. So that also we can monitor with the reanalysis data. Then scientific analysis like process studies, time series analysis, and AML. And we suppose that we were discussing that yesterday, that the first two talks that we were discussing about the observations. So we know that we don't have conventional observation and even satellite observation at each and every point. So when you do the reanalysis, depending on the domain, whether it is global or regional, you will get data where none are observed. So some information you will get about the where there is no observation also. So these are some of the user communities. And what are the different types of reanalysis? There are different types of reanalysis starting from the zeroth generation. So the zero generation reanalysis, then the first generation, second generation, third generation, fourth and fifth. And if you see now that ECMWF is producing the sixth generation data set, that is the ERA 6. I think they may release the data ERA 6 in 2025. And these are some of the that different types of generations of the reanalysis. And if you see, there are many global reanalysis, and these are some of the global reanalysis we can see. So we have global reanalysis from NSERP, then from ECMWF, then from Japan, all those agencies, and we have the regional reanalysis. So if you see IMDAA is one of the regional reanalysis, and we have the KMA, then JRA 25, then like that, sorry, JRA is the global, then NSERP regional reanalysis, and some of the reanalysis from Metofis, SMHI, all those things are in the regional domain. And means the reanalysis, again we can classify that first it is global, and first we can that generation wise 0 to 5th, now the 6th is coming, and we have the global and regional reanalysis and the climate monitoring. So climate monitoring reanalysis means in those type of reanalysis we use all type of available observations. So if you see here, the some of the whatever this green box it is coming. So all this green box thing, it is these are the climate monitoring kind of, sorry, 1 second. So these are the climate monitoring reanalysis. So in this type of reanalysis, you see, for example, in ERA 5 and ERA Indrim, all those things, and in IMDAA and KMA reanalysis, we used all the available observations. So it's not like that we limited to one type of observation or certain type of observation. So for the climate monitoring type of reanalysis, we can use all the available observation. So there is another type of reanalysis, that is climate change. So how much climate change it is happening, for studying that one. So for example, if you see ERA CLIM, and the 20C reanalysis from the NOVA, these are the climate change reanalysis. So because if you see in the climate change thing, they use only the observation available throughout. So for example, in the 20C reanalysis, they used only the surface pressure. So they want to see only the change. It's not for climate monitoring. So there are two types of reanalysis. Actually, reanalysis we are running for a long period. It is minimum of 30 to 40 years kind of thing. So there are climate monitoring. Climate monitoring reanalysis means we use all the type of available observation, and climate change means whatever the data available continuously. So available throughout the period of reanalysis, that only used. So these are the some examples of that reanalysis types. So then come that why do we need regional reanalysis? We have many global reanalysis, But why do we go for regional reanalysis? So if you see the global reanalysis, whatever the available reanalysis, what is the resolution of ERA 5? You might have been using the ERA 5 data. Huh? 25 kilometer, but actual resolution is 33 kilometer. They are providing the product at 25 kilometer resolution. So if you see the global reanalysis, the resolution is very coarse. So if you want to study a particular region, so then we need the high resolution data. So the low resolution global reanalysis are not suited for studying local and regional scales due to inadequate description of mesoscale features. And production of high resolution global reanalysis is very expensive. So we need lot of computing facility, or that we have to account for the cost of computing when we go for high resolution global reanalysis. Then high resolution regional reanalysis is a plausible choice which can represent mesoscale weather more realistically. So then the user product complete multivariate gridded climate data set for users. DA combines model and the wide variety of observation in consistent manner. And regional focus. So when we do the regional reanalysis, so we can do more focus on the regional climate, benefits of high resolution, the resolved orography, high impact weather, and those things we can do. And model evaluation, then we can have the test bed for extended period, evaluation of regional weather and climate model. And only thing for, if you see, if you are using the regional reanalysis or any regional model, you need the boundary condition and the initial condition from any one of the model that has a bigger domain. So boundary condition of the regional reanalysis system has to come from a global reanalysis. So in the case of IMDAA, we use the boundary condition from ERA interim, because we were running the IMDAA in parallel with ERA 5. So that time ERA 5 data was not available. So the best data available that time was the ERA interim. So we used the boundary conditions from the ERA interim. And since we run this IMDAA for 40 to 42 years, so it's not like that we are starting from 1979, you run 1980, then like that. It is not like that sequence kind of thing. So we divide this period into different chunks of 4 years. So then we run different this group of years in together parallelly. So for each the group, that the starting of each group, we took the initial condition from ERA interim, and afterwards the initial condition is from the IMDAA model itself. So only at the starting of different group of years, like it is of 4 years. So each starting ERA, we use the initial condition from ERA interim, and every assimilation cycle, that 6-hourly assimilation cycle, we took the boundary condition from ERA interim. So only the initial condition at the starting of each group of 4 years. Afterwards, it is like the initial condition is coming from our own unified system. So this is what why do we need the regional reanalysis. And when coming to the IMDAA regional reanalysis, it is Indian monsoon data assimilation and analysis. And we already discussed, it is a collaborative project among nationals and our NCMRW of UK Met Office and India Meteorological Department. And we use the state-of-the-art data assimilation method 4D-VAR, and the NWP model is unified model, and producing the highest resolution satellite era regional reanalysis over the Indian monsoon region from 1979 to 2018, and we extended it to up to 2020. And as we discussed, that as a continuity to the IMDAA reanalysis, NCMRW started disseminating near real-time IMDAA-like products derived from the operational NCM model. So there was, if you see, there was considerable growth and improvement in the atmospheric observing system during the reanalysis period of IMDAA, and that helped IMDAA reanalysis, because as in the earlier slide I showed that climate monitoring and climate change reanalysis, IMDAA is a type of climate monitoring. So we used all the available observations, we assimilated all the available observation in IMDAA. So see why it is calling satellite era reanalysis, because you know that first operational satellite, that meteorological satellite, that TOS, it was from 1979. So that's why it is called the satellite era reanalysis from 1979 onwards. So then we have hourly single level field and 3 hourly vertical field at 12 kilometer resolution. and we can download the data from the Reanalysis website. And we have the publication, so all the details are there in this publication. This is open access thing that anybody can download the data, download the paper and go through this one. And coming to the domain, so IMDAA domain, as we were discussing, it is the regional reanalysis, and the domain is 30 to 120 degree east and 15 degree south to 40 degree north. So this is the domain. And lateral boundary condition we used from IRA in RIM because it is a regional model. So we have to update the lateral boundary condition. And data assimilation method is 4D var atmosphere, and we use a soil moisture assimilation also. So we use the extended Kalman filter method for the soil moisture assimilation. And the model is the unified model. Horizontal resolution is 12 kilometer, and even if the horizontal resolution is 12 kilometer, our data assimilation resolution is 24 kilometer. We didn't assimilate the data at this same 12 kilometer, but at a coarser resolution 24 kilometer. So the vertical resolution 63 model levels, and the model top was up at 40 kilometer. And observation source, since we have run this reanalysis from 1979 to 2020, so the observation we took from different agencies like ECMWF. So ECMWF, they were doing reanalysis in Sloan. So they collated all the observation for reanalysis. And since we have the collaboration between Met Office, and Met Office is working very closely with ECMWF, so we got all the observation that ECMWF collected for the reanalysis, and we have our own data source, and from some of the data from UK Met Office, and some of the historical data from IMD. So the historical data archival is one of the main part of this reanalysis. So we got the data sources. This is mainly the observation sources mainly from ECMWF, then IMD, then we have used some of the data from NCMRWF and UK Met Office. And if you see the surface, the soil moisture analysis, we have 4 soil levels of soil covering the first 3 meters in depth. And sea surface temperature, we used the hard SST2 and OSTM analysis. So this is the salient features, this is the domain, and these are the basic features that whatever we use the model, then the lateral boundary condition, and what are the assimilation technique, and what is the model resolution and vertical levels, all those things. So in a nutshell, these are the salient features of IMDAA, and this is the domain you can see. And the timeline of observation, so as we told that we have used lot of observation. So if you see, it is from 1979 to I have shown here up to 2018 because initially it was for 2018. Afterwards we were having almost all the observation at NCMRW. So it's like we didn't go to any agency to get the observation. So here you can see that what are the different types of observation we assimilated. So from 1979 to throughout the period of IMDAA, we assimilated the surface observation. So mainly the SINOP, then buoy, and some of the METAR observations. And similarly, we have the upper air observation like radio sonde, and we have the aircraft observation. So these are the 3 conventional observation we assimilated throughout the period of IMDAA reanalysis. And if you see many of even IRA 5 also, IRA 5 I think now they extended that historically be up to from 1950, but initially it was also from 1979, but now they running the back years also, so it is from 1950. So throughout the period of any reanalysis, we can at least use the surface and sonde observations and the aircraft observation also. So these are the 3 the conventional observation we use throughout the period. And as we were discussing, this is the satellite era reanalysis. So from 79 onwards, we have the TOS. So TOS data, so TOS, if you see TOS and ATOS, there are different, ATOS means advanced TOS. So the number of channels, that instrument, there are some differences, but we use the TOS data from 1979 to maybe around 1999. So after that, if you see, after that we have the ATOS. So when the TOS stop, there is some overlapping period, then after that we have the ATOS data. So we use throughout the period of IMDAA, we use the satellite data. So that's why it is called the satellite era reanalysis. And we use the satellite winds, then the scatterometer winds, ATOS, Severi is the meteosat images, so that also over the Indian Ocean region, that also we used. And MVRI is the predecessor to Severi, that is before that Severi, that it was MVRI over on board that meteosat satellite. Then yesterday we were discussing all about the hyperspectral instruments. So AIRS, ERC and CRIS. So these are the three hyperspectral instrument data we use. So you can see the timeline when we introduce these different types of data. So from 79 to 1999 we have TOS, then we introduced the satellite winds maybe around 1988 or 1989 that time. Then the scatterometer wind, when it's that QSCAT onwards, that we introduced that data. Then ATOS, then whenever the radiances are available, that time when it is become operational, so we started using that data also. So these three hyperspectral instrument we use. These are multispectral. If you see MVRI and Severi, these are multispectral in the geostationary, and ATOS, this is in the polar satellite, and AIRS, ERC, CRIS also in the polar satellite. Then after that we introduced the ATMS, AMSR and SAFIR. So there are some peculiarity of IMDAA, because IMDAA is the first reanalysis that uses Indian data. So many of the Indian surface data we used in IMDAA, and we used the satellite wind, that insert satellite winds we used in the assimilation. We didn't use the insert radiances, because in the operational use also we didn't see much improvement due to the assimilation of the insert radiances. So we didn't use those data in the reanalysis. But the SAFIR data that yesterday we were discussing, it was one of the best satellite by India, Indo-French collaboration. And we are the first to use the SAFIR data in the reanalysis. Even that ERA 5 doesn't use the SAFIR data. So maybe I think in ERA 6 they may use the SAFIR data. So that these are the different observation we used in the reanalysis. So you can see that we used a wide spectrum of data. So that is available from 1979 to throughout the period of IMDAA. And what are the important aspects of IMDAA? So we used many of the historical data from IMD and NCMR WF archival. These data are not available in the ECM WF archival, because if you see from 1979, many of the Indian data, it was not available in the international GTS. So ECM WF archival, they don't have this data, but we retrieved this data from IMD and NCMR WF archival, and we use those data in our regional reanalysis. And use of many satellite observation. And another important thing is the variational bias correction for satellite radiances. So before 2015, till 2015, we were using the static bias correction for satellite radiances. So the bias correction files are static, that with respect to with season or with monthly or once in 3 months, we may have to change the static bias file. So from 2015 onwards, we changed that static bias correction to variational bias correction. So variational bias correction means bias correction of the satellite radiances is part of the Fordyvar equation itself. So there is one more term, and it corrects the biases in the satellite data. So in IMDAA also we use the variational bias correction method. And this uses state-of-the-art Fordyvar data assimilation method, and for the soil moisture assimilation we use ensemble Kahneman filter method. So these are main important aspects of IMDAA. And if you see the use of historical data from various sources, so as we already discussed that the main source is ECMWF, but we got some of the data from NCMRWF and IMD archival. So this is a snapshot for April 2014. You can see this is the NCMRWF SYNOP observation, and this is the ECMWF, and these are the extra observation available in the IMD NCMRWF archival. So these additional observation, but these all observation might not have gone, but after quality control, some of the good quality observations we used in the IMDAA system. So compared to other global reanalysis like ERA 5 or JRA, so the one of the important aspect of IMDAA is the use of historical data from IMD archival. So similarly, we have some of the upper air data also that is not available in the ECMWF collated data for the reanalysis. So this is again a snapshot, conventional observation assimilated. So this is like we were running for 40 years. So you can see this is for 1984, 1994, 2004 and 2014. So just a snapshot from each decade. So here you can see that here it is written surface, sonde and aircraft. So you see that as the time progresses, the number of observations already increased, particularly if you see the aircraft observation. So initially we were having very less observation, aircraft observation over the IMDAA domain. But if you see in 1984, in 1994, the number it is increased, and again it is increased 2004 and 2014. You see there is huge number of observation over the IMDAA domain. Similarly, if you see the surface observation also, but we can see there is a reduction in the surface observation, particularly over the oceanic region. This is mainly because if you see for ERA 5 also, we have checked with ERA 5 how much data they have used. This their plot is almost similar like this, because during the yearly period there were some lot of observation campaigns. So that data also we we received from ECMWF. That's why we have a lot of observation over ocean during the yearly period, but later I think it is somewhat reduced. And here also you can see that the radio sonde observation, upper air observation, there were some campaign during that period. That's why more observation, but later on the number of observation over that region it is reduced. But one thing we can notice is the Tibetan Plateau area. It is there is no observation. It is it is an observation sparse region till today. So we don't have much observation over that region. So when we plan for new observation systems and all, I think we can plan how much new instruments we can that install over this region, and but we have to take care of the difficulties also. So this is the if you see that with time how much improvement that how much larger volume of data we used in the system. So this is the same for all climate monitoring system, because if they are using all the available data, this is the same way. So the initial period there were very less data, but as and when the time progresses, the number of observation both conventional and satellite, it is increasing. Okay, so then if you come to the satellite observation, so this is if you see that these are the satellite instrument we used. So again, if you see, this is TOES. So from 1979 to that around 2000 or 1999, we used the TOES data. So TOES data again from many satellite from NOVA 5 onwards we used, and it is that microwave sounding unit and HIRS. These are the two instruments on board. And afterwards we have the ATOS. So TOES, it is TIROS operational vertical sounder. ATOS is advanced TIROS operational vertical sounder. So then from 2000 onwards we have the advanced TOES, all those things like if you see NOVA 18 onwards, NOVA 15 onwards we have, then all the instrument like AMSU A, AMSU B, HIRS, all those things we used in the reanalysis. And we have other observation like Severi, then other things like ERC and Saphir, all those things. So these are the satellite data we used. If you see, the time frame of IMDAA reanalysis is highly challenging because of the rapid development in the observing system, particularly the satellite observation. So IMDAA used radiances from more than 40 satellite instruments, of which 24 are in the post 2000 period. So in post 2000 we used 20 instruments, that is from only from TOES. So that means 20 instrument in the sense the satellites are changing. So when we count that how many instrument we data from different instruments we assimilated, we used around 24, and post 2000 we used around 16, more than 16 we used. So total more than 40 satellite instrument data from 40 satellite instrument we used in the IMDAA reanalysis. And we know that satellite instruments like any other measurement system are not perfect, and they are prone to error also. So we have to do the error means bias correction. So the erroneous observation can systematically damage the data assimilation scheme. So the requirement of an advanced observation bias correction scheme. So we introduced the variational bias correction. So what are the sources of biases in satellite data? So yesterday also we discussed the biases in satellite radiance vary with time. So depending on the time of the observation, depending on the geography, depending on the air mass and the scan position of the satellite, the biases can change. So as I told earlier, we were using in the operational system also static bias correction. So the time, scan, air mass, all those things we fixed, some fixed value we put in the static file, and depending on the season we change that static values. But here we use the variational bias correction method, so it is part of the data assimilation system. I think in WRF also you have VARBC, VARQC like that, so you can use that VARBC or VARQC as for correcting your satellite data. And nowadays we can use this VARBC and VARQC for correcting the aircraft data also, aircraft and GPSRO data also. So that this is example for the VARBC, how the error is reduced. So this is for Saphir, and it took to that error bias halving time, it is approximately 3 to 4 days. That's what we saw in our assimilation in the IMDAA analysis system. That initially it was not that much reduction in the bias, but afterwards it is it become set with the model, and the error is reduced. So then we already discussed we are using many instruments like TOS. So how that the bias, all those things it is coming. So in TOS 1978 to 2000 or 19 because the period is 1978, but we used from 1979. So MSU, that is in the that ATOS we are telling AMSU A, AMSU B like that, advanced microwave sounding unit. So in TOS it was only MSU, microwave sounding unit. So this is for a particular channel 2. So we have the MSU channel from NOVA 5, NOVA 6, NOVA 7, NOVA 8, 9, 10, 11, 12, 1, 14. Up to these, up to 5 to 14, these are the TOS group. And here you see the R matrix value, that is observation error value we specified is the for this particular channel 2 is 2 Kelvin, and what we found is the RMSE is very much less than this observation error we specified. So RMSE is less than 2 Kelvin. So that the assimilation system it was processing, it is considering treating the data fairly well, and we got the error with respect to the background, it is less than the observation error we specified in the system. So similarly for the ATOS, this is for a particular channel, AMSU B MHS channel 5. Here if you see the R matrix value we specified is 4 Kelvin. Here it is 2 Kelvin, here it is 4 Kelvin, because we inflated the error to account of some more error, means that scan position and geography, all those error to account, we inflated the observation error. And what we found is for this is again NOVA 15, NOVA 18, METOP A and METOP B. So if you see NOVA 15, the error is slightly higher compared to the other satellite. So then the RMSE is between 1 to 2 Kelvin, what we found in the when we did the O minus B and O minus A analysis. So the assimilation system, it was working fine even if we introduce more and more data in between. So there is no jerk in the reanalysis, and everything is a balanced kind of thing, that every time we were checking this whenever we introduce the new data, so we check the status of the assimilation system. And I already told we were running the 4 years together, so to balance that data, because if you see suppose I am running from 1979 to maybe 82, so this is one stream, so in that stream then 82, then 83 I am running for the next stream, so we need to get a balance. So for getting the balance, the next stream we run 1 month prior, so the 1982 December 1st onwards we run, so that there is a balance, because in between we are using the fresh initial condition. So to get the balance and adjusting that what is the spin up, all those things, that we used 1 month overlapping time. So for each every 4-year stream we have 1 month overlapping time to account for the spin up. So daily 4 times. 4 times. So this is how we treated the TOS and ATOS. Here we have showed only one channel, so similar channel also we checked. And if you see the main highlight, we use the incremental 4D VAR. It is Rollins et al. 2007. And one of the major advantage of 4D var is the flow dependent. Why the flow dependent? Because in 4D var we take care of the time also. So we can, if you see the 3D var, if you are running the 3D var and if you are considering the plus or minus 3 hours, but your background is only at 0, or if you are running for the 0 UTC, so you are considering the background only at 0, and all the observation, whether it is 1 UTC, 2 UTC, 0 UTC, you are assuming that it is at 0 UTC. So the flow dependency of observation is not coming in 3D var. But if you see the 4D var, we are taking care of the time of the observation also. What is the when that observation has taken. So the observation flow dependent influence is accounted in the 4D var, and here we use that hourly background field, so that we have that every hour that background field were coming. So then land data assimilation, we already told that extended Kalman filter based land data assimilation we use, and these are the soil moisture layers 10 centimeter. This is the depth 10 centimeter depth, 25 centimeter depth, 65 centimeter and 2 meter. And what we could see, we saw is 10 centimeter and 25 centimeter it is okay, but as we go below that 65 and 2 meter, that it's not that much good data. And it is prepared every assimilation cycle, 6 hour, that 12 kilometer resolution. And these are the DA method. And if you see the reanalysis system flow chart, so this is the full complete flow chart of the reanalysis. So we got all the observation. This again, the observation we got are received are in different format. It is not uniform format. So first we have to convert all the observation into the required format. So ECMWF, most of the observations are in buffer format, and NCMRWF IMD, some of the observation in ASCII, then some in buffer, and OBSTOR is the observation storage. That is a type of format for the unified modeling system. And UK Met Office also we got observation in the OBSTOR format. So some of the thing in the ODB format also, observation database. This is ODB again, it is the ECMWF database only. So we converted all these observations of different types, different format to ODB. So we use the observations in ODB, and we have all this observation with us. All this observation we used from 1979 to 2018. And actually, if anybody wants that observation, I think we can share that data also. So that is available at, because it is the historical observation, that is available at NCMRWF. So we converted all the observation into a uniform format, and background field, it is from era interim. At the beginning of each stream, we are using the initial condition also from era interim. Then we do the observation processing. So the observation processing, we have to do all the bias correction, background check, buddy check, hydrostatic check, all those checks we do. Then we get the quality controlled observation. So after getting the quality controlled observation, we do the 4D var, 4D variational method. That assimilation, this is at 24 kilometer resolution we are doing. It is not at 12 kilometer resolution of the model grid. And similarly, that we have the quality controlled surface observation, we do the screen analysis. Screen analysis we did in 3D var, and after that the soil moisture analysis in extended Kalman filter. And we fed all this data into the variational assimilation system, and from that the short forecast, that is at 12 kilometer. And for short forecast, we need the lateral boundary condition, and it is coming from the Rhine rim, and we need the that lower boundary condition also, that we give the SST. And other thing, it is the soil moisture, and over land the soil moisture analysis is coming, and SST that we use the hardly SST2 and Ostia. And after that, so the boundary conditions are fed, and then the short forecast, then the post processing and dissemination of the data. So the data is disseminated either in GRIP2 or NetCDF format. So this is the full system, that IMDAA reanalysis flow chart. So any reanalysis, if you see, the system is like that. The changes it will come, the observation, in which format you need the observation. Then if it is the global, you don't need any initial condition, because it generates its own initial condition. And how do you do the screen analysis or the soil moisture thing, depending on the method may change, but you need this also. Then again the assimilation system, that is the frozen system. So here we use the 4D var, but in era 5, if you see, that is I think they use the ensemble method also. You will get the probability also from era 5. So the ensemble system they use, so instead of the standalone 4D VAR system. Then the short forecast. So reanalysis means there is no forecast for long period, but you can do the reforecast. You can take the reanalysis data and you can run the forecast. That is called reforecast. But generally, the reanalysis producers, they don't know give the forecast. Only the short forecast they give. So there is only the short forecast and post processing and dissemination. So whatever. Screen analysis, we do that, we have the surface data from that SINOP, buoy, all those things. So since we are not using the actual in situ soil moisture and soil temperature, we produce some pseudo values from the 2-meter surface temperature and 2-meter relative humidity. So from that we do some screen analysis. So that's what, since we don't have, we have the data, but we are not directly assimilating the in situ soil moisture. We are using the soil moisture analysis, only the SCAT thing, so that you, because whatever the available surface observations are there, with that we do some pseudo analysis of the screen, the surface screen temperature using 2-meter temperature and 2-meter humidity. That's what it is, screen analysis. This is a kind of pseudo temperature we are getting. It's not the actual screen temperature. Okay, so then we have to check whether the system is working properly or not. So then we have to see what are the, as we already explained that, discussed that we use the surface data and the upper air data throughout the period of the reanalysis. So we are checking the background and analysis fit to surface observation and background and analysis fit to sonde observation. This is at 500 HPA temperature, you can see. So here what you are seeing is the upper panel is the root mean square error in that for the pressure, that is in Pascal, and the RMS in the temperature, and the count, number of observations assimilated. So this is for the temperature. So if you can see the number of observations assimilated, so from 1979 to this whatever the 2018, there is an increase in the number of observation assimilated. Here we have shown only the surface pressure and temperature. So if you see that surface temperature, we assimilated more observation, but the surface pressure, because it was that from the same station, it might not have passed the quality control. So the number of surface pressure assimilated is less than number of that surface temperature observation assimilated. And here also you can see that here we didn't see much changes, and here O minus B and O minus A. So for a good assimilation system, what we expect is our O minus A should be always less than O minus B. Because O minus B, it is the different innovation in the background, that is observation minus background. And analysis means after assimilating observation, we are getting the better initial condition. So that analysis should be better than the background. So always we expect if the assimilation system is working fine, our O minus A should be always less than O minus B. So here we can see that throughout the period we have that less O minus A compared to the O minus B value for the temperature, and also for the pressure. So temperature, I think we didn't find much difference. It is almost in the same range throughout the period, but within the error limit. But if you see here in the pressure, if you see in the later period, the O minus, both O minus B and O minus A reduced. And here also you can see that even if we assimilated more temperature observation, there is not much change. There are changes, but there is not much, it's not that much visible. But here you can see there is a decrease in O minus AB and O minus A of the pressure, that RMS in the pressure. So this is a good signature that with time our analysis is improving, and both the innovations, background innovation and the analysis innovation also improved when we assimilated the data. So here if you see this is for the 500 HPA observation. Here again you can see this is the first column is the temperature. First panel is the temperature, then second one is the humidity, and third one is the number of observations assimilated. So here that you can see that initial period we assimilated more number of observations. So I showed that spatial plot also. So we were having more upper air observation from some of the campaigns, and later on the number it is reduced, but it is almost same. But here also you can see that in the case of 500 HPA temperature and humidity, we can see that decrease in the O minus B and O minus A. Both O minus B and O minus A are decreasing. So when we assimilated more and more radio sound observations, both O minus B and O minus A, it is reduced, and it is again showing the robustness of the assimilation system we used in the IMDAA reanalysis. And again we can see, yesterday we were discussing about the GPS RO data, because it is we were discussing that it is bending angle or the refractivity, it is the bias free data. So that can act as the anchor observation to reduce bias correcting other observation. Similarly, the radio sound observation can also be act as an anchor observation to bias correct other satellite observations. So that's what we are seeing in this one. So the biases in the innovations in the background and analysis with respect to the radio sound observations, it is drastically reduced with respect to time. So then similar trend in the background and analysis fit of other observation means we can see if you check the IRA5 paper, so that similar type of decrease we can see. So that that almost in all the, whether it is global or regional, all the assimilation system, reanalysis system, the changes are almost similar. So then next is the, so we first we analyze the data assimilation system, the quality control, all those things, so it is working fine. Now we have to see the analysis increment, how much, yesterday we were discussing about the analysis increment. So the analysis increment represents the net response of the data assimilation to all observation used. It is not the particular observation at a particular point, whatever the observation you used in that whole domain, what is the impact of the consolidated impact of all the observation, it is represented in the analysis increment. So the nature of analysis increment provide important information about the performance of the DA system, including the changes in the observing system, and this is a good proxy for the model bias. So if you see, as we were discussing that we introduced more observation in between, like whenever basically the satellite observation, so whenever the new instrument is available, so we introduce that system, that data in the analysis, means reanalysis. So in here you can see that this first panel is the temperature increment, second one is the zonal wind, and third one is the specific humidity. So here you can see that the specific humidity increment, that analysis increment, you can see it is mainly during the monsoon months, the analysis increment is positive. So you can see all these things that periodically we can see that it is again the, we are using a good model. So model is also representing the monsoon properly. So that's why that we are getting the lower level humidity better. So humidity increment. And similarly, we can see that the zonal wind and meridional wind, how meridional wind is not shown here, but the zonal wind increments, whether it is east west or that east or west, that component, that is also that positive and negative it is coming. It's not that analysis increment also not uniform, because we introduced more data in between. And here you can see the temperature. So in the lower levels you can see lot of changes due to the in the analysis increment, and in the upper level also you can see so many changes. So now we can see how these changes are coming. Analysis increment responds to the radiance data assimilated. So here you can see that from TOVs onwards we introduced the satellite data. So here you see, so the TOVs that from 1979 to 90, maybe around 2000 we assimilated the TOVs. So that time in the upper atmosphere around 12 to 13 kilometer, we got some positive changes in the temperature in the analysis increment. And if you see, when we change that to TOVs from ATOVs, that changes in the analysis increment, it is slightly shifted to the middle atmosphere. So maybe from 6 to 8 kilometer, that changes it is shown. So that whenever this changes in the assimilation, means observing system, that is already reflecting in the assimilation system and also in the analysis increment. So here we introduce the ATOs. So these are some of the timelines. So here we introduce the MVRI data, then AMSR2, then ATMS and Saphir, Severi, so then ARC and CRIS. So these are the timeline, and here you can clearly see there are some changes whenever we are introducing new data. So this is a climate monitoring type of reanalysis, and we used almost all the available data set. And the data assimilation system is responding to the introduction of new observations. That's what we have seen. So this is again when you see the IRA5 or NSUB or JRM, almost the same sort of that response you can see in that their system also. So now this is all about the data assimilation system. Now the users, they are not concerned about, they are not supposed to know about all these things, because it is the producer, that whoever is producing the reanalysis, they have to do all the data assimilation, quality control, everything, and the user, what they are using is only the product. So they don't know what are the type of observation we used. So they may be knowing because there is publication, so they have the list, but they are not bothered about how much data we use. They want to use the good quality data, long term data. So then we have to see the what is the quality of our reanalysis also. So we did compare this data with the ERA 5. So this is the comparison. So geopotential height and winds at 150 HPA and rainfall, that is the top panel, and the similarly thing in the 850 HPA in the lower panel. So here we can see that it is for the upper panel, it is IMDAA, then lower, it is 150 HPA, 850 HPA, and October, November, December rainfall and winds 850 HPA for IMDAA, and 150 HPA, 850 HPA, and October, November, December for ERA 5. So if you compare 1 to 1, this is the JJ geopotential height and wind. So we can see that this IMDAA is 12 kilometer resolution. So the resolution impact is already visible in this one compared to the 33 kilometer or the 25 kilometer the ERA 5 products available. And if you see the JJ's rainfall and wind at 850 HPA, so clearly you can see the low level jet, all those characteristics. So that if you see the compare this IMDAA with ERA 5, so we can see almost all the features are represented, means almost similar features we can see. It is one-to-one correspondence we can see in both the product. Similarly for the October number, the winter field also. So we compared the gross features for the 1979 to 2018. This is the average picture. There may be year to year or season to season, there may be some variability. But if you see the mean picture, IMDAA is very well matching with ERA 5. And we did the comparison for other products also, though. So this is the daily precipitation. So here we are showing up to 2018, because initially IMDAA we were planned up to 2018, that's why. So this first one is the IMD observation. Again, we have to see, even though we have run a very high resolution regional reanalysis, we don't have a high resolution data set to verify that reanalysis, because whatever the precipitation data set we are having, that IMD graded data set, it is of 25 kilometer resolution. And if you see the temperature data set, the IMD data is of 100 kilometer resolution. So again, we have to compromise there. So if we want one-to-one that comparison, we have to again extrapolate that 12 kilometer to 25 or 100 kilometers. So that is one drawback. So since we don't have the high resolution data set, we cannot compare that same resolution data set. So here that this is the IMD observation. This is IMD minus IMDAA and IMD minus ERA 5. So here the lower panel, you can see the correlation. So this is the IMD and IMDAA correlation. Actually that correlation, you can see it is 0.5. But if you see the correlation between IMD and ERA 5 also, this monsoon core region, we can see in both the reanalysis, the correlation with the IMD observation is higher. It is coming maybe around above 0.6 like that. But if you see the correlation between IMDAA and ERA 5, there is a good correlation. So mainly in the central India, then over the Western Ghats, over the northern region and northeastern region, that we have good correlation about 0.6. But we can see over the plains, the correlation is less. It is like less than 0.5. So this is what we observed when we compared with the precipitation from IMDAA and ERA 5. So basically the plain, you can see that even if you see the correlation IMD and ERA 5 and IMD and IMDAA, the correlation is less, and even with both the reanalysis, the correlation is less over the plains. And this is for the JJS period, monsoon period. This is for the winter period. So this is again the IMD observation at 25 kilometer, then IMD minus IMDAA and IMD minus ERA 5. So here we can see that during the October, November, December, the correlation with the observation, that IMD observation, it is better, but the ERA 5 is, if you see all over India, it is slightly better. And if you see the correlation between IMDA and IRA5, the correlation is above 0.6, 0.7 like that is coming. So during the monsoon period over the plains, the IMDA and IRA5, it's not matching particularly over the plains, but during the winter season, there is a good match between IMDA and IRA5. And this again, you know that there are excess monsoon and deficit monsoon periods. So we compared that that IMD observation and IMDA. And if you see that actually what we saw is IMDA is the precipitation, it is slightly over predicted, but we don't know whether it is correct or not, because whatever the 25-kilometer product it is available, it is again from that gauge it is extrapolated to the 25-kilometer grid. So that errors in the extrapolation also we have to take into account. But you can see the structure, the variation in the rainfall, all those things are nicely captured in the IMDA also. So this is red line is the IMD observation and the blue one is the IMDA reanalysis. And if you see the excess monsoon period and the deficit monsoon period, that is also captured very nicely. Wherever there is a deficit, the IMDA could capture the deficit, and the excess also it is captured very nicely in the IMDA reanalysis. So this long-term reanalysis you can use for your studies, and it is in general it is matching with the available low resolution observations, and it is able to represent all the monsoon features and the winter features, and it is able to predict the excess and deficit monsoon also. So then we again compared the monsoon onset and withdrawal dates from IMDA, IRA5 and the available IMD dates. So blue is the IMDA one, then green is the IRA5 and red is the IMD. So mostly all this the onset date it is matching, but we have to be careful that we used here for the vertical wind shear index of Prasad and Hayashi 2005, that method we used to calculate the onset from IMDA and IRA5. But when we talk about the IMD onset date, it is highly subjective. So they see how many that there are multiple stations, it is continuously raining, and there are some other many conditions also. If these conditions are persisting for so many days, then they declare the onset date, but there is a lot of subjectivity in that one. So if you consider that also, then we can see that the onset date derived from IMDA and IRA5, it is almost matching with the IMD onset date. So exactly there is not much difference from the onset date calculated. In some years there are some 1, 2, 3, 2-3 days difference, but otherwise it is always matching with both the reanalysis. And again coming to the withdrawal. So withdrawal, we don't have the withdrawal data set from IMD, because the withdrawal it is dates are different. So we cannot say when it is when the monsoon is completely withdraw from the Indian landmass, because along with the southwest monsoon withdrawal, we have the onset of northwest monsoon also. So it is very difficult. But again, we use this vertical wind shear method, and we calculated the withdrawal date from the Indian landmass, the southwest monsoon. And you see that both the reanalysis, we don't have much observation from IMD. But if you see the IMDA and IRA5, both are matching. So both the data set, it is giving the almost same withdrawal dates from 1979 to 2018. So there is a close, these two data sets are closely means matching, and we can use these two data set, that one-to-one correspondence also there. So this is again for the temperature. So here, as I already mentioned, that IMD observation, it is available at 1 degree. So this approximately 100 kilometers. So this is the IMD minus IMDA and IMD minus IRA5. So here we found a difference. This is the daily minimum temperature for December, January, February. So this is for March, April, May. So here if you see, the IMDA minus IMD minus IMDA, if you see, we are getting a positive difference. So that means during winter, IMDA is under predicting the temperature. This is the minimum temperature. So the minimum temperature during winter is under predicted in IMDA, but not that much under prediction, because if you see IMD minus IRA5, it is negative. So IRA5 temperature is more. So compared to the observation, IMDA is predicting a cooler winter and IRA5 is predicting a hotter winter. So the temperature, minimum temperature is slightly different in both the reanalysis. And if you see the daily maximum temperature, that is maximum temperature we mainly say during the summer, that March, April, May. So here also you can see that IMD minus IMDA, it is like negative. So IMDA is predicting a that less warm summer, and ERA 5 is predicting a that is the temperature is higher during summer, the temperature is higher in the ERA 5. So this is the difference what we observed in the temperature data set, minimum and maximum. So otherwise all other field, it is that it is matching with ERA 5, and all the IMDA fields are matching with. And I think this is the inherent problem of the model. So this is the unified model problem. So because if you see the our operational forecast also, and when we compare with the observation, the minimum temperature is slightly less in the our operational forecast, the unified system also, and the maximum temperature is slightly higher. So that we have to do the changes in the model development. That means this is one of the what is that, the drawback or the objective that we got from the means IMDA reanalysis, that this is the temperature problem, the surface temperature problem. So that we have to address in the model development. Okay, so then we did the location specific verification also. So this work was done by one MSc project student from QSAT. So she has selected some 14 locations different over all over India, and she compared all this maximum temperature and minimum temperature, all those things. And the same thing, that whatever we found, that IMDA data shows hotter summer than ERA 5, particularly over the north of 20° north, because over the extra tropics it is showing hotter summer, and cooler winter again over the extra tropics it is showing the cooler winter, because then IMDA is better over south of 20° north in terms of temperature and variable. So other variables, so that means over the tropics IMDA is better, and when we go to the extra tropics north of 20° north, then we are getting the hotter summer and cooler winter. And we think this may be due to that we are not representing the large scale features in the regional domain properly, because they are, even if we are using the lateral boundary condition from the ERA interim, so that how frequently we are updating the lateral boundary condition, that also depends. So the lateral boundary condition we are updating 6 hourly, so that is not much enough to represent all the large scale features in the regional domain. That may be one reason we are getting the hotter summer and cooler winter, so because it is the regional domain. Otherwise in the tropics, so the convection, all those things, it is in situ kind of thing, so those things are better represented in the IMDA regional reanalysis. So then again we compared the data with the OLR, that the outgoing long wave radiation. So this is again we use the Kalpana OLR data, that is at 25-kilometer resolution, and the IMDA data at 12-kilometer resolution. So you can see that on an average this OLR, the high OLR over the Bay of Bengal, low OLR over the Bay of Bengal during monsoon it is matching, and over the Arabian that west coast also it is matching. So the OLR also we can use for as the proxy for the monsoon prediction, those things, that is also good data set. And when we did the, since it is a regional model, a regional domain, so we use the high resolution topography data, that is again 12-kilometer resolution. So we did how this regional reanalysis, it is predicting the extreme weather events. So we analyzed the 2018 extreme rainfall over Kerala. So this is the hourly average, that during that period 6 to 18 August 2018 rainfall. So we have the IMD gridded observation, that is again 25-kilometer. And we have the IMDA 12-kilometer, and we have the RAF5 25-kilometer. So you see that the high resolution regional reanalysis is better predicting the extreme rainfall events even over that region. So we can see that compared to the RAF5, so the observation, and even though there is some changes in the location, that is there, because again you see this is 25-kilometer and this is 12-kilometer. This is again 25-kilometer. So the orography is highly resolved in the regional reanalysis compared to the global reanalysis ERA 5. So then it could better predict the extreme rainfall due to the that orography means the induced rainfall and all. So that's what we found. And as I mentioned that we have two reanalysis over at NCMRW. One is the regional reanalysis with the unified system, and another one is the global reanalysis with the GFS system. So we compared all these three reanalysis, so IMDAA, NGFS and IRA5. And what we found is when we compared the rainfall predictability, so all the three reanalysis captured the spatial pattern of observed rainfall reasonably well in all the season except over the hilly regions. And both IMDA and NGFS captured the probability distribution of observed rainfall intensity, especially the extremes. So we think this is because that we use the available observation over the Indian region in both the reanalysis. So the additional observation we used in the local observation we used in the Indian reanalysis, it helped to predict the extreme rainfall better in the Indian reanalysis than the IRA5. So both IMDA and IRA5 are equally good in capturing the light rainfall also compared to the that IRA5. So that this is another advantage that we use, that most of the available the local data that has not gone into the other global reanalysis, though that is helping us to predict the extreme rainfalls better. It's not that it is actually matching with the actual value, but it is predicting the better value. So this yesterday we were discussing, this is the site and these are some of the publications, and if you see that we have lot more publication. This is the one that this comparing the three reanalysis, IMDA, NGFS and IRA5 against the rainfall observation over the Indian region. And we have another paper that bias correction using the IMDA reanalysis, so quantile mapping bias correction method to IMDA reanalysis for calibrating the NCMRWF unified model operational forecast. So we use this IMDA reanalysis for bias correcting our operational forecast also, because it is a long term one. Then we have so many land surface and hydrological application products. So these are some of the hydrological and land surface application product, but we didn't assimilate any of except the soil moisture and the pseudo screen analysis. We didn't assimilate any hydrological observation, but we have the diagnosed product from this one. So you are free to use this observation, but I think there will be lot of biases, and if you can bias correct the observation, then it would be good. Otherwise, it's long-term data you can use. We cannot guarantee other like temperature, humidity or wind, we cannot guarantee the correctness of this data because it is all are diagnosed from the model. We didn't assimilate much data except the soil parameters. So then these are some of the publications. So sir and his student has done the analysis of soil moisture estimates from global and regional data set over the Indian region. So this soil moisture means data they have taken and they did some study. And another one, the validation and bias correction of solar radiation from two reanalysis products over India. Actually this one, it is representing, they use IMDA and MERA, and they found that there was a lot of bias in the IMDA, and they did the bias correction. After the bias correction, IMDA is better matching with the observation. So we need some sort of bias correction for all the means diagnosed product kind of thing. And this is another paper they are using, they use this data for the some of the agricultural application, revisiting statistical spectral agrometeorological wheat yield model for Punjab using MODIS, EVA and NCMRW free analysis temperature data. So there are a lot of application for this reanalysis. Many, actually initially we never thought of that many people use this for agricultural application and all those things, but now there are many people are using for policy making, all those things they are using the data. So this is the site, and you can register. And actually yesterday I was telling that there are some issues in the site, and means we will sort out those issues, and I think after that you can means uninterrupted data download will be there. Otherwise, if you are facing some issue, please write to me. So we will try to resolve the issue as early as possible. And I just want to show one site. So that is one reanalysis inter-comparison site. You can see that almost all the reanalysis are available there. So here if you see, this is the reanalysis, advancing reanalysis, reanalysis.org homepage. So here you can see there are many types of reanalysis. It is listed, and there are some tools also. So if you want to compare the reanalysis plotting, data manipulation, those things are there. Then atmospheric reanalysis comparison table. If somebody want to know what are the different types of reanalysis available, so those details are there in this table. So ECMW of reanalysis, then we have the Japanese reanalysis, NSUB reanalysis, all those reanalysis, everything is written in this one. And you can use some table, some plotting tools also. I think you need to register for that, and you can compare, you can use two types of reanalysis, and you can plot and see how it is different. Those things are there. So I was mentioning about the 20 CR. So 20 CR, 20 CR version 2, these are the climate change reanalysis, because they used only the surface pressure. So you can just see how the climate change reanalysis and climate monitoring reanalysis, how much difference is there, because ERA 5 is not there now. I think they may add later. And ERA interim is there, JRA 55 is there. So these things, you can play with the data set, how it is comparing, and there are some plotting tools also. So I think you need to register for that, then you can see how much difference between the data set, and if you want to plot some data, that also you can do. And there is one, yesterday somebody was asking about the long-term data set. There is International Surface Pressure Data Bank. So if somebody wants to use that data, that also they can use that. It is only the surface pressure. So it is from 1755 to 2012, means it is very huge, that long term series of data it is available. So it means there are a lot of website that they are providing the long term series, and you can play around the data. So this is one of the site, it compares all the reanalysis. So I will stop here. Thank you.
Any clarification?
Hi, ma'am. So whenever a new observation comes, let's say comes to you, so is that goes into your reanalysis system again?
Now?
No, whenever a new observation, I mean past observations, let's say some observations from 2015, you received it now.
Now I think our reanalysis is over. So we completed the reanalysis run up to 2020. So now we are not modifying the reanalysis.
Okay.
So now means we are not running. It is frozen. So now if we are getting the new, now we have to start another reanalysis, the reanalysis version 2 or something like that. In that only we can use.
And ma'am, you showed some tops and ATOPS RMSE plots. So what exactly do you compare it to against?
No, actually, yesterday we were discussing about the that cost function. So you have two terms, the background term and the observation term, and you have R matrix, that observation error covariance. So you have to specify the error value of the observation in that. So for the TOS and ATOS different channel, that MSU and AMSU, for each channel we specify the error value, observation error value. And we found that error value, we determined that instrument NEDT, some error value will be there. So then the RT model, radiative transfer model, whatever we are using, that some error can come from that also. Like that we accumulate those error, and we gave some specific error accounting all the errors. So for the MSU we gave 2 Kelvin for that particular channel. And what we found is the observation minus background and observation minus analysis, that difference is less than the observation error we have given. That's what. Similarly for the ATOS also. ATOS, because we know ATOS is the advanced one and we want to assimilate more data. Because of that we inflated the error. So we, instead of 2 Kelvin we gave 4 Kelvin. So that some more observation can go into the assimilation, because it is a good quality observation. So that's why we inflated the observation error and we gave 4 Kelvin, and we found that the innovations are less than 4 Kelvin. So that means whatever we are assimilating, that is the good data set. The error is less with respect to the background and analysis.
And I have one more question. So the SST that you used as the boundary condition, so the Ostia SST, it has a temporal resolution of...
it is coarse resolution.
Yeah,
So
it's
that,
a daily SST as per
daily, actually we are updating the SST only at 12 UTC. It's not all assimilation cycle, only once in a day. So 12 UTC only we update.
Okay.
Even now that in our atmospheric deterministic system, we update only once.
So even
Because SST, if you see, there is not, it will not change much. So the day-to-day variation is very less. So once in a day, we update the SST. So we interpolated that to 12 kilometer resolution and we used that one. So SST variation is very less. Now, if you see like atmospheric temperature variation, you can have the diurnal variation. But the diurnal variation in SST is very small. So we don't need to update every time. But if you have the data, you can update, that is better. But in the coupled system, SST is that forecasting. So SST is part of the coupled data assimilation. In that, every cycle we can assimilate. But in the deterministic atmospheric system, we update only once. It is one basically because the data availability, and secondly the diurnal variation is very small unless there is some extreme systems like tropical cyclone or something.
I mean the operational forecast, what SST do you use?
We use Ostia now.
Oh, in reanalysis and the forecast as well. Okay.
Okay. But we are planning for the coupled system, so we simulate the SST also from buoy and other satellite. Then it is the predictive variable. But you mean bias correction in the observation? So, okay, this means IMDAA means whatever the reanalysis bias correction. So, okay, so actually if you see that many of the data like minimum temperature, maximum temperature, then maybe whatever we have shown that solar radiation, all those things, it's that basically the solar parameters, these are all diagnostic parameters from the model. So it is not accurate. So we compared with the in situ values. So we have many that solar flex measurements, and also we compared with those values, and we found that there is a consistent bias in the model diagnosed one reanalysis product. So we can use any type of bias correction method to remove that bias. So it is not like that there is a specified method kind of thing. You can just remove, you just see the O minus B and the observation at the point observation and that location specific bias, and you remove that one. So some linear interpolation or something, that some bias correction method you can use, then it means whatever the bias correction methods are available, it's not that specific. You have to try with that bias correction method. So then you have to come out with the best one. It is like AML only. So you don't know which method AML method you have to use for particular data set. It is different for different data set. Similarly, for different parameter, you have to test different bias correction method and you have to come out with the best one. We cannot specify this is the best bias correction method. So you have to play with that. So because for the temperature, if one bias correction method may work, that may not work for the soil moisture or for the solar flex variables. So it is different. Yeah, that mainly they in that paper you can see how they have used that Condell mapping. If you don't have access, I will share the paper with you. So that means it's not that specific. You have to try and you have to come up with the bias correction method. We cannot advocate a specific method for that one, because even for our operational products we are applying the bias correction. So for precipitation we are applying one type of bias correction. For temperature we are applying different type of bias correction. It's not this. Actually, the post-processing, I'm not dealing with that one. I will check with the verification team and I will inform you what type of bias correction method they are using. Because it is not the same for the precipitation and the temperature. It is different. I will inform you what type of bias correction they are using.
Hello, am I audible?
Yes. Yes.
Yes, ma'am. This is Jagdish Prajapati. I just wanted to know about the static bias correction and variational bias correction. What is going inside the methodology?
You mean the part of data assimilation?
Yeah.
Okay, static bias correction. Actually, if you see the satellite radiance assimilation, the bias correction, the error can come from different whatever the location of the satellite, whatever the scan position, what is the height of the satellite or air mass, all those things it can come. So in the static bias correction method, what we are doing, the errors for this particular each contribution from scan angle, each contribution from air mass, all those things we are specifying a single value, and it is a static file we are keeping. And when we are doing the data assimilation, this static file information is taking, and that either subtraction, addition, or interpolation it is doing, and that type of bias correction it is coming. But in the variational bias correction, what we are doing, the bias correction is the part of the data assimilation itself. So if you see the 4D-var equation, there is a bias correction term also. So it is doing every day we are, it is not the static way, depending on the that actual observation and the background of that particular time, then we are taking and we are correcting along with the variational bias, means variational assimilation method. So if you see the variational bias correction equation, we can see one more term in the 4D-var equation. So there it is correcting, and we are updating one file, that is the VARBC file. So that file will be used for the next assimilation cycle. So that way we are, because it is not a static file. So we have the scan dependent air mass, location, everything is written in that VARBC file. So that VARBC file in each and every assimilation cycle, it is getting updated along with the assimilation. That's what we are using. I can share
ma'am.
the
Thank
papers
you.
with you so that you will get more idea about what is the
Please.
variational bias. You please write to me. I don't know your mail ID. So please write to me. I
Okay,
will
okay,
share the
ma'am.
paper. Okay.
Okay,
So
okay.
both the
Thank you.
things, that the
Thank you so
static
much.
and the variational bias, both the paper I will share so that you will get the idea.
Okay, ma'am. Thank you so much.
Okay.
And one more question, ma'am.
Okay.
In general, actually, I read in most of the papers for the data assimilation purpose, they are usually using short range forecast. Is it
So
because only it is most reliable, or is there any other scientific support for this?
no, actually short-term forecast in the sense, if I'm telling in terms of NCMRWF scenario, we are running the 6-hourly assimilation cycle. So 0, 6, 12 and 18. So if we want to start the assimilation at 0 UTC, we need one background field. You can use the climatology also, but the climatology may not be correct. So I don't know whether you listened today morning talk by Chandrasekar sir. He was
No.
okay. So then in this one, so what we in the operational centers we are using is the best available data. So from each assimilation cycle we are making a short forecast. So maybe you can tell the 6-hour short forecast. So if I am making a 6-hour short forecast from the 18 UTC, what I am getting is that 6-hour short forecast is valid for next day 0 UTC.
Okay, ma'am.
Correct. So
Okay.
at the 0 UTC, whatever I am having is the 6-hour short forecast from the previous cycle, and I have the best available data set. That's why we are using the short forecast, or that is what we call the first guess. So the first guess or the short forecast. So then we do
Okay,
the
ma'am.
assimilation in that first guess. So that is the concept.
Okay, ma'am. Thank you. Thank you so much.
Okay.
So any more questions? So please.
And from there, forecasts are made. So suppose from 00, then we'll have 3-hourly focus files. But in IMDAA, means if model is initialized as suppose 00, it means we get our data as like observations, like 6 etc. We have some all the values of the variables. So in that 6 etc. Is it initialized as 00 etc. and it is a focus file, or it is the
actually that in IMDAA also we did that 6-hourly assimilation. So whatever you are getting, you are downloading from our website. The analysis is only at 0, 6, 12 and 18. And we are telling that hourly single level field and 3-hourly upper level field. So profiles we are telling. So in between that 0 and 6, that between two analysis, whatever you are getting is the short forecast. So in between, it's even it is reanalysis. The reanalysis is coming only at the assimilation cycles. So we cannot run hourly. It is very computationally expensive. We cannot run 3 hourly also. So that's why it's for ERA 5 and all other reanalysis is it's like that. ERA 5 also 6 hourly intermittent. So 0, 6, 12 and 18 you get the reanalysis, and in between whatever you are getting is the short forecast. So 0 is reanalysis, 1, 2, 3 up to 5 it is forecast, again 6 you are getting the reanalysis, then from 7 to 11 it is short forecast, like that.
Well, thank you.
IMDAA has 2-meter temperature data in a hourly basis. How you take the maximum temperature and the minimum temperature of a day in your analysis?
So that it is hourly temperature it is coming, na? So you have to take the 24 hour, each hour what is, then you have to find out what is the maximum value.
From 3 UTC to the 3
No,
UTC of the another.
that you can take according to your convention, whether if you want 0 UTC to 0 UTC you can take like that also. If 3 UTC to 3 UTC, that also you can take, because IMD convention is 3 UTC to 3 UTC, so you can take that way.
Thank you.
So maybe around 14 UTC, 15 UTC you get the maximum. That is the convention, the local maximum it is coming. So earlier we were giving the Tmax, Tmin and all, and then we thought that user can estimate their own value. That's why we stopped. Now we are not disseminating those things. It is only the the hourly values we are giving. So user can download those hourly values and they can extract what is the maximum and minimum. Thank you. So I request everybody to use IMDAA, and even if you are facing problem, please use and give us the feedback so that we can improve the reanalysis. So for the next generation or the next version, we are planning for coupled ensemble reanalysis with much higher resolution, maybe of 4 kilometer. So that's what we are planning for the MOS atmospheric mission. So that's what, maybe for the next 5 to 10 years, it may take time. So thank you.
Dr. Indira, Rani.